Hello everyone, welcome to my YouTube channel. This is Enoch's tutorials. Don't forget to like and subscribe after watching the video so you can receive every update from this channel. In today's lesson, we are going to look at the concept of acid-base theory. That is how some scientists like Arrhenius, Bronsted Lowry, and also Lewis defined acid and base concepts based on the type of reaction they think they undergo. We also discuss some neutralization reactions relating to acid bases and also look at the concept of conjugate acid-base pair. Don't forget to like, subscribe, and share to whom it may concern after watching, so you can all link up and be updated on every update from this channel. So let's begin. So the first concept of acid and base was given by a scientist we called Arrhenius, and he defined acid and bases based on their reactions in an aqueous solutions only. So Arrhenius defined acids and bases based on how they react in an aqueous solution. An aqueous solution is a solution of water. So how acid and bases react with water molecule is how Arrhenius defined his concept of acid and bases. By Arrhenius, he defined acid as any substance that produces hydrogen ions when dissolved in water. Or Arrhenius' definition of acid says that an acid is any substance that produces a hydrogen ion in water or in an aqueous solution. For example, he realized that when you put an HCl in a water, or let's say in an aqueous solution, the HCl breaks down to form a proton, which is hydrogen, and also a chlorine. So since this one produces a hydrogen ion in an aqueous solution, Arrhenius defined HCl as an acid because the HCl produces hydrogen ion in an aqueous or in a water solution. Once again, he defined bases as any substance that produces a hydroxide ion. This is a hydroxide ion formed when a water molecule releases a proton. So when a substance produces a hydroxide ion in an aqueous solution, Arrhenius classified that substance as a base. For example, we have a sodium hydroxide. Sodium hydroxide in water produces a sodium molecule, which is Na plus, and also OH minus, which is a hydroxide ion. So per his definition, since sodium hydroxide produces a hydroxide ion in an aqueous solution, he classified sodium hydroxide as a base. Aside, you can have potassium hydroxide, calcium hydroxide, or even aluminum hydroxide. All these substances produces hydrogen or hydroxide ion in an aqueous solution. Hence, he can classify those substances that produces hydroxide ion in the aqueous solution as a base. The next scientist is what we call a Bronsted Lowry. And Bronsted Lowry defined acid and bases based on their reactions in aqueous and non-aqueous solution. The first one, Arrhenius defined his own based on their reactions only in aqueous solution, but Bronsted Lowry defined acids and bases based on their reactions in both aqueous and non-aqueous solution. So how they react in water solution or any other non-aqueous solution like any organic solvent is how he applied or how he used to define acids and bases. According to Bronsted Lowry, he said an acid is a proton donor and also a base is a proton acceptor. So in an aqueous solution or in any solvent, if a substance donates a proton or gives out a proton, that substance qualifies to be called an acid according to Bronsted Lowry. So from this one, as we define according to Arrhenius that HCl can produce hydrogen ion in an aqueous solution, it can also donate proton in an aqueous solution and even in non-aqueous solutions like organic solvent. Hence, HCl qualifies to be called an Arrhenius acid and also a Bronsted Lowry acid because HCl can produce or can donate a proton in an aqueous solution. Once again, a water molecule itself can donate a proton in a solution to form an H plus and a hydroxide ion. So a water molecule qualifies to be called an acid according to Bronsted Lowry. Also, an ethanoic acid. An ethanoic acid can produce a proton or can produce a proton or donate a proton in an aqueous and non-aqueous solutions. So ethanoic acid also qualifies to be called um, a Bronsted Lowry acid. Some ions like hydronium ion or ammonium ion can also donate protons in an aqueous and non-aqueous solutions, and these ones also qualifies to be called a Bronsted Lowry acid. An anion like when a sulfuric acid gives out one hydrogen, it assumes a one negative charge here. This ion also can donate a proton in an aqueous solution to produce SO2 or SO4 2 minus. So this one can also give out a proton or donate a proton in an aqueous solution. Hence, HSO4 minus also qualifies to be called a Bronsted Lowry acid because it can give out a proton or donate a proton in an aqueous and even in non-aqueous solution. These ones are anions because it carries a negative charge, and these ones are cations because it carries a positive charge. These ones are neutral molecules, and since they can all donate protons in an aqueous solution, they all qualified to be called an acid according to Bronsted Lowry. Now, how we define protons or bases is that bases accept protons in an aqueous and non-aqueous solutions. So molecules like water molecule, ammonia, chlorine ion, hydroxide ion, and ethanoate and sulfate all carries lone pairs of electrons that allows them to accept protons. So this one qualifies to be called a Bronsted Lowry base. So Bronsted Lowry acid says that for them they donate protons in an aqueous and non-aqueous solution, and bases accept protons in aqueous and non-aqueous solution. So all these molecules have lone pairs of electrons that allows them to accept electron or accept proton or hydrogen ions. So when they accept proton, they form what they call a dative covalent bond. And the dative covalent bond is a bond formed when one species engages in the bond or donates all the two lone pairs of electrons in the bonding system. So when they see this chlorine accept a proton, forms an HCl, and the bond in that HCl or in that chlorine hydrogen is donated by only chlorine ion. So in this case, that bond is called a dative covalent bond. So these ones have lone pairs of electrons. They contain at least one lone pair of electrons to form a dative covalent bond with protons. All these compounds or all these ions and molecules accept protons, since they qualify to be called a Bronsted Lowry base. The next one is what called Lewis acid. So Lewis acid defined his concept of acid and bases more widely applied to systems with and without solvents. So the first one, Arrhenius defined his own in an aqueous solution only. Bronsted Lowry defined his own based on aqueous and non-aqueous solutions, whereas Lewis defined his concept of acid and bases based on whether it is in a solvent or it is not in a solvent. According to Lewis, he said an acid is an electron pair acceptor. When any molecule can accept an electron pair, that compound qualifies to be called an acid. So an H plus has no electron. A BF3 can accept two pairs of electron. A aluminum chloride can accept electrons, and also beryllium chloride can also accept electrons. All these species can accept electrons, hence they qualify to be called amino acid according to Lewis. For them to be able to accept electrons, they must be electron deficient. So according to Lewis acid, all electron deficient species are acids because they all have the tendency to accept electrons. Lewis acid can also be called electrophiles because electrophiles are compounds that are very deficient electrons and have tendency to accept an electron pair. So H plus is an electrophile, this is an electrophile, this is an electrophile, and this is an electrophile. Hence, they all have tendency to accept protons in aqueous, non-aqueous, or even solutions or environment without any solvent. So Lewis acids are electron deficient species or electrophiles. According to Lewis, bases are also electron pair donors. So for him, he said acids are electron pair acceptors. Therefore, the donors of these electron pairs are what he classified as bases. Compounds like an ammonia, a hydroxide ion have two lone pairs of electrons that enable them to donate the electron to form a dative covalent bond to form a stable molecule. So if you have an H plus, which is a division of electrons, plus OH minus with two lone pairs of electrons, here this OH minus can donate this electron to this H plus. In this case, here act as the acid, here act as the base, or this one act as an acid, which is, or let's say, an electrophile, an electron deficient species, and he just want to act as a nucleophile, which is an electron rich species, to form a water molecule. So in this case, the OH donates electrons to the H plus to form the water. Hence, OH minus qualifies to be called a Lewis base. The same if you have a BF3 plus an ammonia. The ammonia has two lone pairs of electrons as shown here. So the ammonia can donate the electrons to BF3 to form this complex. In this case, the two electrons linking the ammonia and the BF3 were all donated by the NH. So this one, since this one is an electron pair donor, according to Lewis, an NH3 qualifies to be called a base because it donates electron to the BF3 to form this complex. Reactions between acids and bases always forms a neutral compound, which is a neutralization reaction. So in this case, all Lewis acids are electrophiles because they are electron deficient species, and all Lewis bases are nucleophiles because they are electron rich species. So these are the three main definitions of acids and bases given by three scientists. That is Arrhenius, who said acids and bases, they produce hydrogen and hydroxide ions in solutions. Bronsted says that acids are proton donors, whereas bases are proton acceptors. And Lewis says that acids are electron pair acceptors, whereas bases are electron pair donors. So let's look at the concept of a conjugate acid-base pair. A conjugate acid-base or conjugate base or conjugate acid is a compound formed when there's an interconversion of a proton between two compounds. So when we take this compound like this, if you have an HCl plus water giving you chlorine minus plus a hydronium ion, this is a typical, let's say, a neutralization reaction between an acid and a base to produce, let's say, here's a salt and more of a water. So here you can say that this HCl acts as the acid and donates a proton to the water molecule, leaving the chlorine ion here as minus and the water molecule as a hydronium ion. Now, let's take the forward reaction. In the forward reaction, this one acts as the acid and the water molecule acts as a base. Whereas in the backward reaction, the chlorine ion acts as the base and the water molecule acts as the, or hydronium ion acts as the acid. So when you have this one, this is an acid. When it gives off this proton to the water molecule from hydronium ion, the resulting ion is the conjugate base of the acid. So here the acid is HCl. When it gives off its proton to the water to form a hydronium ion, the resulting ion is the conjugate base of the acid. In the same way, when we take this compound like this, when we take this one, this reaction, this base accepted the proton from this to form this compound. So the hydronium ion becomes the conjugate acid of the water molecule. So in a nutshell, if an acid gives off a proton, the resulting compound is called a conjugate base. And if a base accepts a proton, the resulting compound is called a conjugate acid. So in summary, this is a conjugate acid of this. In the backward reaction, if this is the base and it accepts the proton from this one to form this one, this is the conjugate acid of this. At the left side, this is an acid, this is a base. At the right side, this is a base and this is an acid. So take note of the two definitions. A conjugate acid is a compound formed when that acid donates a proton, and a conjugate base is a compound formed when that compound accepts a proton. So you can say that a conjugate acid-base pair is a pair of species that can be interconverted by transfer proton. So here, between this chlorine ion and an HCl, they can be interconverted by proton transfer, either gain of this one or losing of the proton to this. So there's an interconversion between chlorine ion and HCl by protons. In the same way, there can be possible interconversion between water molecule and hydronium ion. So these two are conjugate acid-base pairs. Let's look at some typical chemical reactions. So a species can behave as an acid or a base depending on the situation, as we define here. So depending on the environment of the compound, it can make it behave as both an acid or a base. So let's take this compound in which water acts as different compounds altogether in the two reactions. In the first reaction, the water here acts as the base by accepting a proton from the chlorine to form a hydronium ion and the chlorine minus. But in the second reaction, you can see that the water acts as the acid and donates a proton to the ammonia to form an ammonium and a hydronium ion. Here you can see that the water molecule here and this one are the conjugate acid-base pair, where this one is the conjugate acid and this one is the conjugate base. Here you can see the water acts as a conjugate base here and here as a conjugate acid. Here it acts as a base and here it acts as an acid. So based on the environment of the compound, it can make it behave as an acid or a base. Let's look at some typical concept of conjugate acid-base pairs in the following reactions. HCl plus water gives you a chlorine ion and a hydronium ion. In the first reaction, this is the acid, this is the base. Then this is the conjugate base of the acid, and this is the conjugate acid of the base. In the second reaction, this is the acid, this is the base. This one is the conjugate base of the acid, and this is the conjugate acid of the base. In the third reaction, ethanoic acid plus water gives you an ethanoate and a hydronium ion. This is the conjugate base of the acid, and this is the conjugate acid of the base. Once again, you can have two water molecules interreacting by itself. So the first water molecule gives a proton to the second one to form a hydronium ion, and this one leaves a hydroxide ion. So the hydroxide ion acts as the conjugate base or the first conjugate acid, which is the water, the red one. Then this one, which is the conjugate acid, is the conjugate acid of the conjugate base here. Let's take this one too. That is a disulfate ion plus water molecule, giving you a hydronium ion and a sulfate. So this is a sulfate ion. This one becomes the conjugate base of this acid. Then this one becomes the conjugate acid of this base. Thanks for watching. Don't forget to like and subscribe to watching the full video, and also share to whom you may consider. You can receive every update from this channel. Thank you.